Welcome everyone to this video that will discuss implicit differentiation. We're going to explain how this method is slightly different from methods we've seen before. When a function's y value is obtained through a direct relationship or a rule that depends only on x, we can say that y is an explicit function of x. For instance, here are examples of functions where y is directly obtained from calculations on functions of x. These functions we tend to label as f of x or g of x or h of x, and it's clear who h, f, and g are and how y depends on them. So all these are explicit. Many relationships, however, can relate two variables, x and y, without being explicit. For instance, the equation of a circle, x squared plus y squared equals 1, does not actually show how y depends on x. All we see is an equation where we have to assume that changing the value of x will force you to change the value of y accordingly. That's also true of the other functions that are listed there, and whose shapes are obviously not circles anymore. So some relationships among those shown above are not even functions, they're relations. However, in every single relationship that appears, the value of y does have to adjust to the value of x when this one is changed so that the equation is satisfied. The way in which y will react to changes in x is harder to figure out because it's not an explicit derivative we'll be doing. Y is not expressed explicitly in terms of x and therefore requires a special attention and method. The equations that we saw are called implicit equations. Given that y does change when x changes, one can presume that its rate of change can be evaluated as well. The method used to find the rate of change of y with respect to x is called implicit differentiation. Within implicit differentiation, we are performing derivatives and assuming along the way that y acts as functions of x, at least in the neighborhood of the point AB where the derivative is taken. For instance, here's a circle, which is clearly not a function. But if we focus on one point called AB and visualize only the curve in the neighborhood of this point, well, in the neighborhood of AB, we do have a function. And therefore, there's got to be a way to find the rate of change at point AB, or if you prefer, the slope of its tangent line, or if you prefer, its derivative. So if we assume that y acts as a function of x in a neighborhood around AB, then we can think of y as y of x, or f of x, or g of x, or even as u, if you remember the chain rule. That is, that y depends implicitly, so we're presuming that it depends on x. As a result, any derivative applied to y will require the use of the chain rule, as it is treated as a function of x. More specifically, when we'll differentiate expressions that depend on y, the chain rule will be applied. So the derivative of f of y will be f of y times y prime, just like y plays the role of a u in our traditional chain rule. And by the way, dy dx is another way of saying y prime. So notice how this resembles delta y over delta x. It's a change of y with respect to x. It's the slope of our tangent line. For example, differentiating sine of x, that's an explicit case. Derivative of sine of x is cos of x directly, basic rule. Derivative of sine of y, we're assuming y is actually a function of x, or a function that depends on x. So we're treating it like a u, cos of y times y prime. Explicit expression, e to the x prime, stays e to the x. Implicit function of x, so we're assuming in the y's x's are hiding, e to the y prime is e to the y times y prime. And here is, for the power rule, how the difference between an explicit expression and an implicit expression would differ. So, some guidelines to follow when you perform implicit differentiation. So differentiate both sides of your implicit equation with respect to x. Terms that are explicit functions of x are differentiated like usual. Functions of y are differentiated using the chain rule, as we assume that y depends implicitly on x. We will regroup all terms with y prime on one side of the equation and those without on the other side. And then we'll factor and isolate y prime. For instance, here's an example we're going to look at together. Let's find y prime, so the slope of the tangent line, given that x and y have to satisfy the equation x cubed minus 3xy squared plus y cubed equals 3. This is not a curve that we know how to draw. It's not any of the basic functions that we know. But yet we'll still be able to find a rule for the slope of its tangent line. We're going to start by following the guidelines, which say to differentiate both sides. So I wrote prime, but in reality we have to think we are differentiating with respect to x. So we're treating x as an independent variable, and y is a variable that undergoes changes when x changes. So that's an implicit relationship. First step, I'm using the addition and subtraction rules to split up the terms. Second step, I'm using the product rule to split up the middle term as a product. So I'm treating 3x as f and y squared as g, and we are using the product rule, f prime g plus f g prime. The only reason why there are minuses in front of both is that we are actually subtracting the term 3xy squared, which we have differentiated. Now, going back to the previous slide, the first expression, x cubed, is differentiated. That's a function of x explicitly. We see only x's. So we differentiate that like usual, 3x squared. Second term, we're differentiating 3x. That's an explicit expression of x as well. So derivative of 3x is 3. Here's our first implicit expression. We see y squared, but you should really think u squared. Remember, y depends on x. We just don't see how. So the derivative of y squared is 2y times y prime. Last of the terms on the left side, the derivative of y cubed, that's also a function of y, where y depends on x implicitly. So that's a chain rule, 3y squared times y prime. And the derivative of 3 is 0. There we go. So chain rules forced us to differentiate functions of y and generated the y primes out of it. Now, our next guideline was to simplify, if possible, the terms you have, regroup all terms with y primes on one side, and those that don't have y primes we can push over to the other side. So I've regrouped terms with y primes, and I've actually also factored y prime already on the left. And then we can divide by the term y prime was a factor of. In this case, it turns out that we can even factor a 3 from the top and the bottom and simplify the expression we get for y prime. So that would be y squared minus x squared over y squared minus 2xy. And that's the expression we get for y prime. This is the recipe that will give you the slope of the tangent line to the curve. Notice how the derivative we found depends on both x and y coordinates for the point where the slope is to be evaluated. So we're going to have to supply the x and y coordinate of the curve where this measurement takes place. For instance, if we wish to have the slope of the line that's tangent to the implicit equation that you were provided with earlier at point 21, first thing we would do is, well, potentially verify the point actually fits. So a point that is on a curve should make the equation true, and in fact it does happen here because 2 cubed is 8, minus 3 times 2 times 1 is 6, so 8 minus 6 is 2, plus 1 cubed does give 3. So the coordinate point you're given actually fits the curve. Now what's the slope at that moment? Well, for that we've built a recipe. We've built our derivative formula through implicit differentiation. So at point 21, y prime is obtained by replacing all of the x's by 2 and all of the y's by 1 in the recipe we built. In terms of notation, notice how I wrote y prime at p. Okay, so it's not a general rule, it's the slope at point P specifically. And in this case, we get a slope of 1. So this curve is increasing when it passes through point 2, 1. If necessary, higher order derivatives can also be obtained through implicit differentiation. For instance, in the example we just observed, if you were asked to find y prime prime at point P21 for the same curve, well, you would first of all do the necessary steps to find the first order derivative, y prime, and recall that we have already found the slope specifically at P, which was equal to 1. So these will be building blocks towards finding y prime prime, so the second order derivative. If y prime is equal to y squared minus x squared over y squared minus 2xy, so if these two quantities are the same, then differentiating both sides is a legal operation. It maintains their equality. On the left, we're getting y prime prime, so the second order derivative. On the right, there is a quotient rule that we're going to have to apply. So f prime g minus f g prime. So let's see if we can guess what those individual primes or those individual derivatives will turn into. So first term being differentiated is y squared minus x squared. Okay, it's a subtraction rule, so we can individually differentiate them. The derivative of x squared is an explicit term and will turn into 2x. The derivative of y squared, however, is an implicit function of x. We treat y like a u, so derivative of y squared is 2y y prime. At the extreme right hand side, we have to differentiate y squared minus 2xy. Okay, so the derivative of y squared is 2y y prime. It's an implicit function of x. Visually we see y's. Behind the scenes, x's are having an effect on the y's. So we're treating this like u squared. 2u prime, in this case 2y y prime. 2xy is a product, and we'll have to do a product rule to it. So 2x prime y plus 2xy prime. And here is our outcome. So notice on the right-hand side that we've applied a product rule, which explains why there are two terms rather than one. All right. We wanted to obtain the second order derivative, not in general. Actually, in general is the result you have at the top, but we want it explicitly at point 2, 1. So we're going to replace every single x we see by a 2. We're going to replace every single y we see by a 1. And we're going to replace every y prime we see by the value that y prime takes at point P. Luckily, that's why we calculated it in the first place, and we found its value was 1. So we're reusing the slope already calculated at point P. Inserting that into the result we have in front of us, we'll find that y prime prime at P is minus 2/3. All right, so what does this mean graphically? We have a y prime equal to 1 at P, so the function is increasing. Y prime prime at P is minus 2/3, so a negative second order derivative means concave down. Let's see if that can be seen graphically. All right, so I've used an online software here to obtain what the function what the equation you were given looks like graphically. As you can see, this is not a function at all. It's a relation. Point 2, 1 is located on the curve at this point. Now we said that it was increasing, and of course it seems to match. In fact, it looks like the slope is equal to 1, or the slope of the tangent line. The second piece of information we gathered was that y prime prime is minus 2/3. So it should be concave down and therefore remain under the tangent line, and that certainly seems to be the case.